Ever feel like you're drowning in data? You know, like you're trying to make a simple decision. Should I buy this gadget? Is this health advice legit? But every article you read just sends you down another rabbit hole of conflicting opinions and confusing statistics. It's overwhelming, really. Well, that's why we're here, doing this deep dive. Today we're tackling this head-on with a paper called Statistical Modeling, the Two Cultures. And honestly, it's one of those reads that can fundamentally change how you think about data and knowledge itself. Don't worry, it's surprisingly accessible, even if the title sounds a bit, well, academic. The gist is this. It digs into this almost philosophical clash in the world of statistics, about how we go from a jumble of numbers to actual understanding. The author, Leo Breiman, lays out these two main approaches, two different cultures, if you will. Data modeling and algorithmic modeling. Think of data modeling like detective work. You're a statistician, and you're on the hunt for the hidden equation, the formula that nature uses. What's the exact relationship between rainfall, hours of sunlight, and how tall that sunflower grows?
It makes me think of those old school detective movies, with the detective hunched over his clues, trying to pinpoint the culprit.
Yeah, and in this case, the culprit is the true model, the perfect equation that explains the data. Now, on the flip side, we've got algorithmic modeling. This is less about finding that perfect formula and more about building a machine that just flat out predicts the future, even if we don't fully get all the gears turning inside. Think of those recommendation algorithms, right? They seem to know what you'll want to watch or buy next, even if you don't get how.
It's funny you mention that because Breiman himself, he wasn't just some stats whiz living in the abstract world of equations. He actually had this whole career as a consultant before returning to academia. We're talking real-world, messy data problems.
Yeah.
Oh, yeah. He consulted on everything from predicting ozone levels, which back then was a huge deal for public health alerts, to identifying compounds using this technique called mass spectrometry.
So he'd actually wrestled with the messiness of real-world data before diving into the theory.
Absolutely, and that comes through so clearly in the paper. He's not arguing that one culture is superior to the other. Instead, he's saying both data modeling and algorithmic modeling, they're tools in a toolbox.
Okay, I like that. So it's not a competition. It's about choosing the right tool for the job.
Exactly. And to illustrate, let's look at one of the projects he worked on, the ozone prediction one. Back in the 70s, you had these really complex data models trying to predict ozone levels. They were crammed with all sorts of meteorological data, but they just couldn't predict accurately enough to be useful for those public health alerts.
So even with all that fancy data and complex models, they were missing the mark.
Yeah, the real world can be a lot messier than any model, no matter how detailed. But then contrast that with another problem Breiman tackled, identifying the presence of chlorine in compounds using mass spectrometry.
Okay, so completely different field, different type of data.
Right. And what's fascinating is that for this, he found that simpler decision trees, think of them like flow charts if this, then that, if this, then that, were incredibly accurate. We're talking 95% accuracy in predicting the presence of chlorine. Sometimes a simpler tool, if it's the right fit for the problem, can outperform a much fancier one.
It's like trying to use a sledgehammer to crack a nut. Sometimes a simple nutcracker is all you need. It's like, okay, we have all these different tools, but how do we know which one to use? When is a sledgehammer better than a nutcracker, statistically speaking?
Well, that's where things get even more interesting. Breiman, he points out this, almost a faith some statisticians have in data models.
Faith.
Yeah, like they see these models as the ultimate truth, a perfect reflection of how the world works.
Which, if you find that perfect equation, it's tempting to think, this is it, case closed.
Right, but that's where those blind spots can sneak in, especially these days. We're drowning in data, right? And data sets with way more variables than data points.
Yeah.
Trying to capture all that complexity in a single equation, good luck with that.
Okay, so too much data, not enough model.
It's like trying to stuff a giant octopus into a tiny teacup.
Okay, I'm getting a visual. But how does that lead to misleading conclusions?
Imagine you're doing a study, right? You've got 50 different lifestyle factors, and you're trying to see if any of them are linked to, let's say, how well people sleep at night. Just by pure chance, some of those factors are going to appear statistically significant.
Just random noise.
Exactly.
Yeah.
But with a data model, it's really easy to latch onto those significant findings without questioning whether the model itself is really capturing the whole picture.
It's like finding a correlation between the number of pickles someone eats and their IQ. It might be statistically significant, but does it actually mean anything?
Right. And Breiman, he brings in this fascinating example in the paper a study on gender discrimination in salaries.
Always a hot topic.
Totally. So these researchers, they create this big data model trying to predict salary based on all these academic performance variables, publications, teaching evaluations, all that.
Sounds thorough.
And the gender coefficient, it pops out as statistically significant.
So discrimination proven.
Well, hold on. Here's where those data model blind spots come in.
Ooh.
The model might seem to show clear evidence of discrimination, but without digging deeper, you could be totally misinterpreting things.
Okay, so how do we know if the model is leading us astray?
It's about asking those tough questions. Like, what factors were not included in the model? Maybe years of experience, field of study, those could play a role.
Right, or even unconscious biases in those teaching evaluations.
Exactly. Without considering those nuances, that statistically significant result could lead you down the wrong path.
So it's a good reminder, even with data, context is king.
Absolutely. And that's not to say data models are inherently bad, just that in this age of big data, we need to be super aware of their limits.
Okay, so where does that leave us? If data models aren't always the answer, what's the alternative?
Well, that brings us to the other side of the coin, those algorithmic models. What if, instead of trying to nail down nature's perfect equation, we just focus on building a machine that's really, really good at predicting the future?
Even if we don't fully understand how it works, like those neural networks that seem to be everywhere these days.
Exactly. It's a totally different way of thinking about modeling. It's not about finding that one true model, that holy grail equation. It's about finding the model that just flat out predicts best, even if we don't have a neat step-by-step explanation for why it works.
So less detective work, more engineering. We're building a prediction machine, even if it's a bit of a black box.
Right. And one of the most intriguing examples of this is something called random forests.
Okay, every time I hear that, I imagine like a magical forest where the trees whisper statistical secrets to each other. Okay, every time I hear that, I imagine like a magical forest where the trees whisper statistical secrets to each other.
It's a fun image, isn't it? But it's actually a really elegant idea. Instead of one big, complicated decision tree, imagine a whole bunch of them, hundreds, each trained on a slightly different subset of the data.
So it's like a diverse forest, with each tree having its own little bit of knowledge.
Yes. And like a real forest, this diversity makes the whole system more resilient. See, each tree makes its own prediction based on the data it's seen, and then the forest as a whole, it kind of takes a vote.
A statistical democracy.
Exactly. And this wisdom of the crowds approach with all that randomness built in, that's what makes random forests so powerful.
Okay, so I get the forest analogy, but in the real world, does this actually work better than just having one really sophisticated model?
That's the thing, it often does. Breiman, he lays out all this evidence in the paper, showing how random forests outperform other methods on all sorts of tasks, from deciphering handwritten text to analyzing genetic data.
So even in areas where traditional statistics kind of hit a wall, these forests can find those hidden patterns and make these really accurate predictions.
Exactly. It's like the forest is able to see the bigger picture that the single tree might miss.
It almost makes you rethink that whole Occam's razor idea, right? That the simplest explanation is usually the best.
It's counterintuitive, isn't it? We're so used to thinking simpler is better, but here we have these more complex models that actually give us more accurate results.
So it's a trade-off then. We might get better predictions, but we might lose some of that easy-to-understand interpretation.
Right, and that's the heart of the debate Breiman is highlighting. With algorithmic models, we're often giving up a bit of interpretability for a big gain in predictive power.
Which, in a world overflowing with data, that predictive power can be incredibly valuable.
Absolutely. And even though these algorithmic models might seem like black boxes, Breiman argues that we can still squeeze out valuable insights.
Yeah.
For example, they can tell us which variables are most important for making those accurate predictions.
So even if we don't have a perfect equation explaining the why, we can at least see what factors are most influential.
Exactly.
Yeah.
And that can lead to new discoveries. Breiman, he talks about this one study where random forests actually helped uncover a hidden subgroup within a data set of patients with liver disease. This subgroup, it had distinct characteristics that traditional analysis had totally overlooked.
Wow, so they were able to find something completely new, potentially leading to better understanding and treatment of that disease just by using a different modeling approach.
It really highlights the potential of these methods.
It makes you wonder what other hidden patterns are out there, just waiting for the right tool to uncover them.
And that's really the beauty of this whole discussion. It's not about picking one right way to model the world, but about having a diverse toolbox and knowing when to use which tool for the job.
And maybe, most importantly, it's about approaching these tools, these complex algorithms, not with fear or suspicion, but with a sense of curiosity and willingness to embrace the unexpected. Because who knows what incredible insights we might uncover if we're open to new ways of seeing the world through the lens of data. And on that note, we'll wrap up this deep dive. We hope this has given you a new perspective on the world of data and modeling. Until next time.